In this talk, we speak of a power spectrum density of a stochastic process. So what it is, the power spectrum density, or PSD? Well, intuitively, it is how much energy there is in the process with frequency. But if we wanted to get for the true definition, we take an observation, so a piece of a realization that lasts 40 seconds, we do the Fourier transform, we compute the squared value of the amplitude, we do the expectation, and we compute the limit of this divided by t as t goes to infinite. So, pretty complicated, but there is an important property that the power spectrum density is a Fourier transform of the autocorrelation. And as this is a power spectrum density, if we integrate all the power spectrum density in the frequency, we have the total power of the process. But as the integral is the autocorrelation in the origin, so the total power is the variance plus the square mean value. When we have two processes, we generalize the power spectrum density in the same way by computing the expectation of the product of the Fourier transform of one process and the other complex conjugate. So this is a cross spectrum between the first process x and the second process y, that is the one we complex conjugate. This is called the cross spectrum, and it is the Fourier transform of the cross correlation. For white processes is a particular case of process in which the power spectrum density is constant. Well, in the continuous case is not constant from minus infinite to plus infinite, but it could be constant only in a limited bandwidth. And it can have also delta in the origin that represents the mean value of the process. So the autocorrelation of a white process is either impulsive plus a constant, or, for limited bandwidth, a sinc plus a constant. Interesting to see that the sinc null in a time that is inverse of the bandwidth, and this is the correlation time. Well, here I show some example, a couple of examples of a realization of a white process. The first, we can hear it. Let's play. And the second, it's a bidimensional process that this way when it is white. Let's now make the case of discrete processes. Well, the definition of power spectrum density does not change significantly. We have to compute the Fourier transform, we have to divide the Fourier transform by the number of samples we considered, and we make the square amplitude, the expectation, and the limit for infinite sample, and this is still the power spectrum density of a discrete process. A little different is the power, because the total power we should not integrate from minus infinite to plus infinite, because discrete signals are limited in a bandwidth that in this case is minus 1/2 to 1/2. And this is the example of the power spectrum density of a discrete signal that is a constant between minus 1/2 and 1/2. It can be a delta in origin whose value is the square mean value. And then, if we do the inverse Fourier transform, that is the autocorrelation, we see that the autocorrelation is impulsive plus a constant. So, an uncorrelated process is a white process with constant power spectrum density. It is interesting now to understand how we can estimate the power spectrum density. Well, there are two ways that follow. The first, the definition of power spectrum density, and the second, the property of the autocorrelation. So, in the first case, we take the piece of realization we have, we do the Fourier transform, the square amplitude, and this is a power spectrum density estimate. This is called the periodogram estimator. The other is an indirect method, because we take the signal, we need first to compute the autocorrelation, then do the Fourier transform, and what we get is the estimate of the power spectrum density. This is a little more complicated computationally, and then it is a little less popular. Let's now consider the periodogram estimator. This estimator is by far the most popular because it is incredibly simple. Simple as doing the Fourier transform of the signal and computing its square value. Of course, this is not the definition of the power spectrum density because of two limitations. One is in blue, we don't have an average over the realization, and one is in red, that we don't have the extension for infinite observation time. Both these limitations will bring errors that we will consider in the future. Basically, these errors are a limited spectral resolution and the spectral leakage, and the random noise that is a power spectrum density. So, let us now consider the case in which we compute the power spectrum density of a sinusoidal process. We have only one realization. Actually, we have only a piece of one realization for a time interval t. T0 is the period of the sinusoid. So we know that the ideal power spectrum density should be two pulses located at the frequency of the sinusoid. But if we compute the periodogram, then we have a different result depending on the value of the observation time t, and in particular, if t is long, very long, then we have many cycles in the observation time. We see that this power spectrum density is not perfect, but very good, because we see the two peaks that are distinguished, and we see this effect of side lobe, that is actually the spectral leakage, that is still a disturb, but is very, very low. Otherwise, if the time of observation is very small and maybe even smaller than the duration of the cycle, then our periodogram gives a power spectrum density estimate that has really nothing to do with the original process. In fact, we see only one peak where we expect two peaks, and we see a lot of spectral leakage. So in this case, we can conclude that the key number is the product of the frequency by time, by temporal observation, should be bigger than 1 to have low spectral, good spectral resolution. So far, we consider the spectral resolution. Now let us speak about spectral noise. And to do this example, we consider a different process, xt, that is made of a sum of two processes. One could be a good signal, like a sinusoid, and the other can be a noise, that in this case, it's a zero mean normal noise. In this case, both signal and noise have the same power. On the left, I show a realization of the signal, a realization of the noise, and the signal to noise. So from the signal to noise, it's very difficult to tell that there is a sinusoid, and even if you can tell the sinusoid, it's very difficult to measure the frequency, for example. On the right, we have the periodogram in two kinds of flavor. The first is just we make the analysis of one sequence. In the second, we average 200 of sequences. And you see that with one sequence, we see the two peaks, and we see that they are distinguished, but we see a lot of disturbance due to the spectral noise that is a contribution of the second process. In the second, as we have averaged a lot of sequences, 200, we see that this statistical fluctuation is very, very small. Still, we see the two peaks and the spectral leakage. So, in any case, we can tell that the power spectrum density estimator by the periodogram is very effective in analyzing the sinusoid, tells us the value of the amplitude and the frequency, but of course, we need a lot of time in order to have good spectral separation. Otherwise, if we do only with one snapshot, we have a lot of spectral fluctuation, so we need a lot of measure to average. And now is a compromise, because let us assume that I have a total of 1,000 samples. What we can do? We can, for example, consider to use only one periodogram with a full length of 1,000 of samples. And this is a result. So we see that the two peaks are very, very narrow because the spectral frequency, the spectral resolution is perfect. However, you have a lot of spectral fluctuation due to the noise. Otherwise, we decide to play with 1,000 samples in different ways. So we cut into pieces of 10 periodograms, so 10 sequences, each of 100 of samples. We see that now the spectral resolution and the leakage is not as good, but however, the spectral fluctuation has been reduced strongly. So in general, there is a compromise in which we can choose to make a lot of periodogram that is very good for the noise. This is a lot of periodograms, the spectral noise goes to very low value, or we can use a very long sequence, but in this case the number of periodogram is small, but we have a very good spectral resolution. And now let us make an example from the real world. Here we have two stoves and the gas, and you have the sound of the gas. The stoves are different because one is very small and one is very large. And let us play the two signals. This is the first signal. And this is the second signal. You see that the periodogram of the two signals are different. And as you heard, the two signals in our brain seems different. Well, in fact, they have a different spectral signature, and our brain exactly analyzes the spectral signature of this signal. However, if we make just one periodogram, we see a lot of detail, but it is very noisy. And it could be a much better analysis if instead than processing all these 10,000 samples in one, we could process much less sample, make periodogram and then average, and we have this. Now the blue and the red curve correspond to the small and the large stove, and you see that there are many features that are in common, but other features that are different between the two signals. For example, this peak is present only in the large stove. This peak has about 4 kHz. And the spectral signal now it's much better defined and they are much better separated so that we can now really classify and detect if this is large or small. And in this case, we have two different spectral signatures and distinguish the two signals. Last but not least, how we can make a digital spectrum analyzer, that is a device that estimates the power spectrum by a do-it-yourself. First of all, these are the components. You can buy on the web, they are very inexpensive. This is a dongle that is called RTL2832, costs a few euros, that scan what is in the air, so transmission, radio transmission, and convert into digital signal. Then you need a PC, this dongle is a USB stick. Then you need a PC that is running an open free software like SDR++, that is software-defined radio, and then the output is the power spectrum estimate. Well, what does really this spectrum analyzer? Take the input signal, divide it to 4 pieces or 3 pieces, for example, and each piece is given in input to the discrete Fourier transform. That is a very effective Fourier transform code. And in this case, the output of the discrete Fourier transform are exactly the frequency output. You just need to square its value and you have the digital spectrum. Of course, when you run time by time, you are also providing a new sample to the discrete Fourier transform, you compute the energy, and so you see the energy changing with time. In this case, you are scanning the FM broadcast spectrum around, for example, 100 MHz, and what you see here is the signal, the contribution of the different FM radios, and this is a power spectrum that says how many transmissions are in this range in this moment.